the inner workings of the universe by dissecting it into smaller and smaller components. Uncovering the laws of nature in the forms of mechanisms, structures, and correlations. It's a stunning fact that all these laws can be described using the language of mathematics. Big breakthroughs were made when physicists realized how seemingly unrelated phenomena could be described using the same mathematical laws. In fact, they simply were different manifestations of the same law of nature. In 1687, Isaac Newton unified the force that causes everyday objects to fall with the force that holds celestial bodies in their orbits. The law of universal gravitation was born. In 1865, James Clerk Maxwell realized that electricity, magnetism, and light could all be described together in one unified theory, electromagnetism. Then, in the early 20th century, two revolutionary concepts changed the way we see the world. Einstein's theory of relativity brought about the notion of space-time, with the speed of light as an absolute speed limit and time that flows differently for observers moving in different ways. Einstein's general theory of relativity expresses gravity as deformations in space-time, explaining how the universe functions at large scales. In parallel, quantum mechanics changed our perception of the world at the microscopic scale, from a strict and precise clockwork-like system to a strange place governed by probability and uncertainty. The study of the laws of nature continued in parallel at the two extremes. The theory of relativity led to a number of spectacular predictions like black holes and gravitational waves that have now been observed in nature. Decades of studies of particles and their interactions led to the establishing of the standard model of particle physics that unifies two of the four known interactions, the electromagnetic and the weak force, into a single electroweak theory, and describes the third interaction, the strong interaction, in the same language. But even electromagnetism still holds some mysteries, like the hypothetical existence of fundamental magnetic monopoles, particles that are just a single north or south magnetic pole. Quark-gluon plasma is a state of matter governed by the strong interaction, where quarks and gluons are not confined within hadrons. It's crucial for understanding the early universe moments after the Big Bang, and can now be reproduced and studied in particle accelerators. The fourth interaction, gravity, is not included in the standard model at all. Developing a theory of quantum gravity that successfully unifies quantum mechanics with general relativity remains an outstanding challenge. In addition, there are a number of features in the standard model that arise without an explanation. The fundamental building blocks of matter are 6 quarks and 6 leptons, arranged in 3 families, but we don't know why there are exactly 3 of these families. We understand the mechanism that gives these particles their masses since the discovery of the Higgs boson in 2012 and the studies of its properties that followed, but the mechanism does not predict the values of these masses. We can measure them, but we cannot explain where they come from. The lightest of the matter particles are the elusive neutrinos. We know their masses are not zero thanks to the discovery of neutrino oscillations. But those masses are so small, we haven't been able to measure them directly. And they cannot be explained by the Higgs mechanism without adding extra particles or mechanisms to the standard model. The Higgs mechanism itself leaves many questions open. Puzzles such as the shape of the Higgs potential and its implication for the stability of the universe and the unnaturally low mass of the Higgs boson inspire new theories beyond the standard model and extensive experimental studies of the Higgs particle. All matter particles have mirror images in the form of particles of antimatter. Matter and antimatter should have been produced in equal amounts in the Big Bang, but if this was the case, today our universe should be empty, since matter and antimatter annihilate when they meet. Instead, the universe appears to contain mostly matter. Some unknown mechanism tipped the balance and more matter than antimatter was produced. That little excess is all the stars, galaxies, everything we see around us. In addition, those stars and galaxies and all matter that we know only account for a tiny fraction of the energy and mass in the universe. From the way galaxies rotate, we know that they must contain a new kind of matter that we call dark matter. We observe how dark matter bends and lenses light traveling between galaxies, but this matter is not made from quarks or leptons. While dark matter could account for the extra mass we observe in galaxies, the accelerated expansion of the universe needs some new mechanism to be explained. Referred to as dark energy, it is thought to make up about 70% of the universe's total energy. Its nature is one of the greatest mysteries in physics. What is the next step? Do all particles have some inner structure that we haven't yet observed? In string theory, they can be described by tiny strings vibrating in different ways. String theory also predicts the existence of additional spatial dimensions beyond the familiar three, but each way in which these dimensions could be shaped gives rise to a potential universe. So is the one we live in just a special case of a vast landscape of possibilities? With new clues from experiments and further developments in theories, the quest to make our universe a bit less mysterious continues.